All right, so the last part of chapter 11 is about radical polymerization. And we'll briefly do an overview of some common polymers, and then we'll discuss the mechanism in a bit more detail. So the first thing you need for radical polymerization is you need what's called a monomer building block. And for these examples, all of our monomers are going to be alkenes. And then what you do in an industrial setting is you get a big pot of these monomers together, and then you polymerize them, often using some sort of special catalyst. And you also need a radical initiator. And when you polymerize these, you convert the alkene, meaning the double bond, to a big long chain of alkanes. So if we think about this, I'm going to bracket it out like this. The left carbon will still have those two R groups on it. The right carbon will have the other R groups. And the brackets on the outside just indicate that there's some repeating unit. And sometimes what you'll see in the bottom corner is you'll see a number indicating that this repeats 10 times or 100 times or 1,000,000 times, indicating how long that repeat unit is. Does that make sense? All right. The mechanism's pretty interesting. We'll cover that next, but I wanted to show you some of the common ones that you encounter in your day-to-day life. Oops, sorry, I should label this as our polymer. All right, so the first monomer we're going to look at is this one where we've got 4 hydrogens. Thanks. Does anybody know what the name of this compound is? So if you follow the IUPAC rules, people like to call it ethene. Most chemists won't call it that, and it's not acetylene. Acetylene's with the triple bond. Instead, people will call it ethylene. It just sounds a little, it just sounds a little bit better than ethene. All right, so you can take ethylene, you can polymerize it, and you can get these big, long chains out where you've got hydrogens coming off all of your carbons. And this can repeat a number of times into the hundreds of thousands. This polymer is obviously going to be called polyethylene. Does anybody know what polyethylene is found in? Plastic bottles. So if you have like a plastic water bottle, chances are that's made out of high density polyethylene. That's the more rigid bottle. So soda bottles that are made of plastic are made of that. There's also low density polyethylene. That tends to feel almost waxy. So if you ever, I guess, grab a water bottle while you work out, like a bike water bottle, those are often low density polyethylene. So those have a different amount of branching occurring in them. All right, so commercially, that's the biggest one in our planet is polyethylene. The next one is pretty similar. However, one of the positions is going to be replaced with a CH3, and this is called propylene. And just like before, you can link these together into one giant polymer. The left carbon will still have 2 hydrogens. The right one will have 1 hydrogen and 1 methyl group. And this will be called polypropylene. Does anybody know what polypropylene is found in? Yeah, so cold weather clothing is often made of polypropylene. It's cheap. Does anybody know why polypropylene is much better for cold weather than cotton? It doesn't kill you when it gets wet. Cotton, when you're wearing cotton and it gets wet, makes you really, really cold. Polypropylene will still absorb a lot of your body heat even though it's wet. So oftentimes this is found in outdoor clothing. It's also found a lot in carpets. So most carpets are made of polypropylene. So another really big commercial plastic. All right, next one is one of the most controversial ones, at least as of late. So instead of a methyl group there, it has a phenyl group, which I'm just going to abbreviate as PH. This is called styrene. So styrene's the monomer here. Just like before, we can show our giant long polymer where we have two hydrogens coming off the left, and then off the right we've got a hydrogen and we've got a phenyl group repeating. This is called polystyrene. Does anybody know what polystyrene is found in? Styrofoam. So styrofoam cups, styrofoam packing peanuts, things like that are almost always polystyrene. Does anybody know why there's such a big controversy surrounding polystyrene? It spends a long time to break down, and it's not really recycled at all anywhere in the world. The reason they don't recycle it is it's so light and takes up such a huge amount of volume that it's just economically not worth anybody's time to recycle it. So they're trying to develop alternatives to polystyrene. So sometimes if you order materials, let's say from Amazon, you may notice the packing peanuts feel a little bit weird. Oftentimes those are made from biodegradable plastics. Yep.
So why is it so much lighter then? Because it had, because on molecular mass wise, it's double to triple?
Yeah, you're exactly right. So the main reason that it's lighter has to do with the way that it's formulated into the product. So they blast air into it. So really it's just a bunch of air pockets in between the plastic. Make sense?
Yeah.
Yeah. All right, the next one, if we look at, is another common one that you'll encounter. This one has a chlorine coming off of it. This is called vinyl chloride. And vinyl chloride, if you polymerize it, does the same sort of thing. We'll make one giant chain that repeats. The left carbon will have two hydrogens. The right one will have a hydrogen and a chlorine. Yep?
So are PCBs considered like are those a polymer, like polymerization, or the polycarbonate by are the ones that it's like baggy and plastic or whatever?
Yeah, so there's a huge number of different plastics. The ones I'm throwing out here are just the most common commercial polymers. There's also condensation polymers that we're not even going to cover right now. Those are the other big ones. So like nylon is a condensation polymer. Same thing with Teflon, or sorry, not Teflon, Kevlar is also a condensation. So if we take vinyl chloride and we polymerize it, we get polyvinyl chloride. Does anybody know the more common name for polyvinyl chloride? PVC. So this is most commonly referred to as PVC. What's PVC found in? Pipes. A lot of the pipes in your home, specifically the drain pipes, taking wastewater out of your home, are made of PVC. It's a really nice polymer because it lasts an incredibly long time. However, it is pretty hazardous to make, so the workers that handle vinyl chloride monomers have to use an abundance of safety precaution. All right, let's do the last one. Another controversial one. This one is tetrafluoroethylene. Same thing, if we polymerize this, we get a big long chain that looks a lot like ethylene, but the main difference is we've swapped out all of the hydrogen for fluorine atoms. So naturally, the name of this one is tetrafluoroethylene. Oftentimes, you'll see on the label PTFE, so that's the abbreviation. Does anybody know the brand name of this? Give you a hint, think of nonstick cookware. Teflon. So this is the polymer whose brand name is Teflon. What makes Teflon great for cooking? Does anybody know? It's non-stick, and the main reason for this is it's very hydrophobic. So things like oils don't want to stick to it, and neither do water for that matter, and that has to do with the weird nature of carbon-fluorine bonds. Does anybody know the downside of Teflon?
It's horrible for you.
It bioaccumulates in our environment. We really have this problem of fluorinated hydrocarbons persisting and bioaccumulating up ecosystems. So we're trying to phase it out. The other problem with this is the manufacturing of Teflon is incredibly dirty and hazardous for the environment. I would encourage anybody that's considering buying Teflon to reconsider and maybe look at cast iron. Cast iron is amazing and also is nonstick if you take care of it really well. This is also a big deal for those of you that ski. A lot of these perfluorinated hydrocarbons are in ski waxes and they bioaccumulate as well. So it's also a big deal with the ski industry of trying to find waxes that aren't fluorinated. All right, I'll get off my soapbox now. Any questions about all these polymers? Yeah.
Are we gonna have to know these and test?
So you will see on the practice exam, I had an example of a polymer and I said, what monomer would you need to make that? So that would be fair game. I'm not going to expect you to memorize names though. Yeah. I just think it's interesting because oftentimes we see these names thrown around, but we never stop to think about what the structure is of these polymers. All right, so let's jump into the mechanism. All right, so the first step of any radical mechanism is the initiation step. And the initiation can vary depending on the type of plastic or the company making the plastic. But oftentimes what you have is an alkoxy radical, which looks pretty similar, right? We use this for anti-Markovnikov hydrohalogenation. And in that first step, we're going to pop off an oxygen onto each side, so homolytic cleavage. And this can actually be accomplished with heat. So we'll get one radical here, and then a second radical over here. So we've got two different oxygen radicals floating around. All right, and then in the next step, we're going to take our monomer. Actually, let me do it over here. And for this example, I'm just going to use ethylene, since it's one of the most common polymers, is polyethylene. And next, what we're going to do is have this do addition to a pi bond, just like we saw with our reaction with HBr. All right, so now we've got our two hydrogens down here. And we've got our radical coming off that rightmost carbon. Does that make sense? All right, so now we've initiated our reaction. Next step is propagation. And propagation, if you remember, is where we take our initial radical, in this case right here, and we react it with something new and we regenerate a radical in the process. Okay, so we'll take that same radical that we just made. Where we still have all of these hydrogens. And then we'll treat it with more of our monomer that's floating around in solution. So we'll have ethylene floating around. And just like before, we're going to use this radical electron and add it to a pi bond. Then the other electron is going to get dumped to the carbon on the right. All right, so we've regenerated our radical. We've just lengthened the starting material by 2 carbons. So you can imagine if you've got more ethylene around, you can repeat this process over and over and over again until you essentially run out of monomer or just shut down the reaction. So for example, this unpaired electron could add into another equivalent of our ethylene. And I'll just show all of our hydrogens for good measure. So really this propagation step is very important, but every time we do that addition to a pi bond, we gain 2 additional carbons, right? So we're not going to have an odd number of carbons in this situation. All right? So you can do this until you run out of a monomer or until you quench the reaction with some sort of radical inhibitor. And then after that, you need to account for your termination. So if you remember, your termination step just means that you're getting rid of your radical. So for example, we might have this repeating monomer unit where we've got some sort of chain length like this. I'm not going to draw all of the hydrogens for this one. And this could find another radical. It looks like this. And these 2 radical ends could just bump into one another and form a new covalent bond between them. So this bond right here is our new linked polymer. Specifically, you call this cross-linking, when you have 2 polymers basically link up together in order to form one long chain. This can even happen almost in a web arrangement where you form almost like a spider web of polymers linked together. Does that make sense? Alternatively, you could have a different one where you still have the same radical floating around, but maybe you've got more of another radical floating around, and these 2 could bump into one another and form a new covalent bond. All right, so either of these termination steps will work. In fact, some polymers, this last one's pretty common because what they'll do is they'll decorate the end using some sort of special end cap. So it's not necessarily going to be the same as your initiator. There's a huge amount of termination steps. I don't really expect you to get into the fine details of all of these possible polymerization reactions. All right. One complicating side reaction is important for these plastics, and this has to do with side branching. And side branching is really important for polyethylene in particular. It can change the structural properties of polyethylene depending on how branched it is. So let's take a look at how this occurs. And the big thing to note is that this occurs during propagation. All right, so let's say we're doing our propagation step. And we've got this alkyl radical like this. what could happen is it could find another polymer chain that's floating around in solution. So to show this other polymer chain, I'm going to use a different color. And this polymer chain has a bunch of hydrogens floating off of it. So it's a separate strand floating around in solution. Let me clean this up. All right, and in this next step, instead of finding another monomer to do addition to a pi bond with, it's actually going to do a hydrogen abstraction of an existing polymer. Let me zoom out a bit. Oops. Sorry. So there we go. We've got our hydrogen installed on our terminal end. Oh my goodness. Let me spread this out. You can tell I don't do a lot of polymer chemistry. But now our radical is located on the inside of another polymer chain. All right, and then in this next step, this polymer, the blue one, can find an ethylene monomer and then do addition with that monomer. It's about how I feel right now. All right, and then this can react with more of your monomer. So for example, I could add in here, keep on going over, but we'll just say etc. The main thing to note though is now we've got branching right here that's coming off of some interior part of our chain, not just lengthening the ends, if that makes any sense. Chemists have gotten really good over the years of controlling the amount of side branching in order to control the more broad physical properties of a specific plastic. All right, so that's the big takeaway for this. This affects physical properties. Yep.
So just note that wasn't a note, that was another section. Note kind of implies small section of page.
Yeah, this is more of a big note. Yeah.
Is there a way to specifically promote the side branching? Like you want it to happen a lot?
Yes, so there's various catalysts you can use to really impact side branching. So if you want a ton of it, you can add a specific catalyst. If you don't want very much side branching, you can use a different catalyst. We're not going to really get into that too much. That's a whole separate field of chemistry. In fact, the biggest field in organic chemistry is polymer chemistry, based on market worth. We just use so much in terms of plastics as a nation. That's where the most jobs are. You hate plastics? Is that because of... Yeah, they're terrible for the environment, that's for sure. If you are interested in reading about this, I'll see if I can find the article and email it out. There's a lot of debate about recycling lately. Does anybody know why? With plastics, at least? So that's part of it. We used to just ship all of our plastic and recyclable materials to China. And this past year, the Chinese government said, you're cut off. No more. We have our own garbage problem here. We're going to deal with our own junk before we start importing other people's junk. So now we've been accumulating a ton of plastic in a lot of port cities, including Seattle, and they don't quite know what to do with it because we don't have the infrastructure to handle that volume. And there's been debate about what to do, and one of the new hot things that they're talking about is actually incinerating plastics. Believe it or not, you can get an enormous amount of energy from just simply incinerating plastics. So it'd be similar to having like a natural gas plant. And then they put big scrubbers on their smokestacks to make sure that none of the nasty stuff got into the air. So that's one valid argument that maybe we shouldn't even be recycling, maybe we should incinerate them. The other one is taking these big polymers and actually putting them in this ultra high pressure vessel, and you can actually do the reverse reaction and then get your monomers back out and then repolymerize that monomer. The problem is that's incredibly tricky to pull off, because if you have this slight contaminant, you could throw off the whole system and have to throw everything out. So there's a lot of work to be done with recycling plastics. Yep. Yeah. All right. All right, so really that's it for the last part of this chapter, was the polymerization. Like I said, if I give you a monomer, I want you to be able to predict what that polymer would look like. Or if I give you a polymer, I want you to predict what the monomer was that was used to make that plastic. The mechanism, I will say, is pretty similar to the hydrohalogenation mechanism. So make sure that you really do know that one. This type of chemistry is not synthetically that useful for a lot of the stuff we'll be using, though. All right, so if we go to the end of the chapter, there's a summary of reactions. There's three main ones you should know the mechanisms for. So there's the radical bromination of alkanes using bromine and UV light. There was anti-Markovnikov addition of HBr to alkenes. We saw that mechanism. And then there was allylic bromination using NBS. We saw that mechanism. So these are the three mechanisms I really want you to know from this chapter and know when to use them for various synthesis problems. Yep. NBS can be used with heat as well. So you might see UV light or heat with NBS. Yep.
Can you use the NBS for the bromination of alkanes, or is it only for the allylic bromination?
It's only for allylic bromination for the most part. Yeah, it's really only used for that. The one thing you might also see in our textbook is if you have a system that looks like this. This is pretty similar to an allylic system where you have this alternating double single bond arrangement, in which case you can brominate the benzylic position pretty easily using the exact same reagent. So NBS and heat. And you can get bromine to be installed right at that benzylic carbon. So you may see that on sapling as well. We'll come back and learn about reactions at benzylic positions later, though. Yep.
On the sapling, it says, like, when it uses NBS, it says UV light or roar. Do they do the same thing?
Or roar?
Yeah, on the bottom.
That's weird. Normally it's UV light or heat. I don't know why they would have had peroxides in there. Yeah, that's odd, though. All right, so that's where we'll stop today. I would recommend trying to get started on some of these synthesis problems. That tends to be the hardest section on the first exam for students, so make sure you really spend some time working on those.